Good day, everybody. I hope you're doing very well. In recent videos, we have been talking about things like Taylor's theorem and the error associated with estimating a function with a polynomial. Trying to figure out a way to quantify that error was a point of concern. And in the very last lecture, we talked about a couple of really simple ways that you can measure differences and explain and measure error in that way. But oftentimes we're going to need some way of talking about the error associated with um, a particular function or quantity of some sort as a parameter grows very large or grows very small. And this is something that is known as asymptotics. We're going to need a bigger discussion about what it means for a function to grow large because it can do so in different kinds of ways. I drew some pictures on the board behind me, and you can see we have different kinds of functions that are going off to infinity in different ways, and that are going in towards zero in different ways. The behavior helps to define what's happening with that function. So we need to talk a little bit about something really useful, and it's called asymptotic order, and there's a tool that goes along with that. That sounds kind of funny. But let's change scenes and get started in that conversation. That tool that we're going to need to kind of describe how a function is changing as it grows very large or very small, etc., is actually something that's called big O notation, which is somewhat less exciting than it sounds at first, but we're going to get into a careful definition as we go forward here. So here's how we want to define it to begin with. Let's have a couple of different functions here, f of n and g of n. And these are functions that I'll say depend on some large parameter. It's a little bit floaty, but essentially we're talking about the growth of those functions, the comparative growth of those functions as that n grows large. Okay, so we need a couple of things here. Let's suppose that f of n and g of n both go to infinity as n goes to infinity. What we say is that f of n is in so an element of is what this weird symbol here looks like, but don't worry about that. It is what it is. And then we have big O of g of n, this thing right here. Or you might just write f is an element of big O of g. And here's what the definition is, and we'll get through it and then we'll parse it together in a second. This is true if there exists some capital N. It's some positive constant. So think of big N as some constant, and if the little n is bigger than the big N, so bigger than that capital N, think of it like a threshold. If little n is bigger than that threshold, we have that the size of f is less than or equal to the size of g. That's what these absolute values are saying. The absolute value of f of n is less than or equal to the absolute value of g of n times some positive constant k. And of course, this should be a positive constant to make sure that this inequality can even hold. But this is what we need, okay? We say that that f is an element of big O of g, or sometimes we'll say f is on the order of g if this definition is true. Okay, I want to think about what this says and maybe talk about this in the context of, maybe the functions that I have on the board here, or just some different straight up language. This is saying that eventually, if n is large enough, so think of it as n is the input, the input to the function. If you're big enough in that input, then eventually f is less than or equal to some multiple of the g. So if I take a look at, say, let's see, this function right here that's crawling up more and more slowly here. It's in green, but I don't think you can see that because the color is a little bit, the picture's small. And we have this linearly increasing function right here. Okay, we can see that at the start, maybe this one that looks kind of like a square root function, the one that's going up more and more slowly, might even grow faster than that linear function at the start. But eventually, there is an x value, or an input value, an n value here in this definition, where that linear function beats that square root looking function, okay? So where that linear function is such that it's the g in this definition and the f is the square root one, because I can see that the size of f is less than or equal to the size of g, maybe times 1, for some n values past a certain threshold. That's what this is saying. It's giving us a measure of uh, um, what the ultimate growth behavior of the function really is. And that existence of a capital N is kind of that threshold where, like, beyond that, we have that this inequality is true, which tells us what's happening beyond a certain level. It's a little bit complicated sounding. However, one thing that we can use to evaluate these a little bit more simply is the fact that, well, we're talking about behavior that's eventually happening. And if we talk about a parameter getting large, that sounds a whole lot like a limit. So what you want to do is, in fact, check to see if one function is on the order of another, if f is on the order of g, by evaluating this limit. This limit right here, the limit as n goes to infinity of f of n over g of n, this compares the relative sizes. I said relatives, but I want relative sizes of f and g as the n grows large. There are a couple of different possibilities here, but essentially, if that limit evaluates to a finite constant, then that means that the f and the g are that f is on the order of g, is what I really mean to say. And it can be shown that if that limit evaluates to a constant, that f must satisfy the criteria for above. If you think about it, we have examples from first year where we can see if that's the case. Suppose that f is, something like x squared, and g is, suppose, 3x squared. And you have a limit as x goes to infinity. So I want you to consider this for a second. This is really kind of comparing two parabolas, right? X squared and 3x squared, which is the same as x squared but with a stretch. The idea behind big O notation is to say that, well, the way that x squared increases as x grows really large, the way which 3x squared increases as x grows really large, they're really the same. They both grow like parabolas grow as x grows really large. And you can see quite well in this definition that if I wrote down the absolute value of f less than or equal to k times the absolute value of g, well, I would get the absolute value of x squared is less than or equal to k times the absolute value of 3x squared. And I can easily see that if k is equal to, well, 1/3 or anything bigger than that, that this is automatically true. And wouldn't you know it, if you evaluate this limit, well, you end up with 1/3, which is a positive constant. And because it evaluates to a positive constant, that tells us that x squared is on the order of 3x squared. It turns out that 3x squared is also on the order of x squared, but with some different constants and so on. And it's really just a measure to say that one function grows quite like another one does as the parameter gets very large. So it's a little bit weird, right? Because we're talking kind of about, how a function generally grows. We're kind of talking about a function in a more hand-wavy, sort of general way, rather than pinning anything particularly down, right? You can show that any two parabolas with any two constants in front are on the order of one another. But then you can create kind of a hierarchy of different functions, that some grow smaller than others, and so on, okay? So that limit has to, so I guess I want to say here, so we could say, so I kind of crafted a random example here, but we could say that x squared is on the order of 3x squared as x goes to infinity. I'm just going to put that in a bit of a cloud. I think it's nice to have that bit of a demonstration here. We have a bunch more examples coming, but it is. I want you to think of it like comparing the growth of different kinds of functions as a parameter grows. Okay, and so I said this above, that really you want to think of it, this notation, you have like an element of, and you have like some weird notation. You want to say f is on the order of g as n goes to infinity, or f is big O of g as n goes to infinity. One of those. Okay, some different things here that I want to point out is that there's a little bit of a different notations that are used here. They do tend to be a little bit of an abusive notation or some hand waviness. For example, some sources might say f equals big O of g, but it's really weird to say that because big O is kind of talking about a whole class of functions that could fall into that. So I prefer the using an element of notation, but just wanted to give you a heads up about that. There are some times when the limit on that previous page gives you 0. And in that sort of situation, it is the case that f grows much less quickly than g, right? Imagine up here that if you put the f over the g, and the limit that you take as n goes to infinity gives you 0, that means from first year calculus that the bottom is dominating. The bottom is what's growing most quickly. And in that case, you don't want to think of f as growing pretty much like a g. It's more that g grows much more quickly than f. And so there's a couple of different things that we can say about this. First of all, for one function to be on the order of big O of another function, you want to think of it as saying the first function grows no more quickly than the second kind of function. That's kind of how you want to think about it, which means that it could grow much less quickly, or it could grow at about the same rate, or having about the same sort of behavior. But in the case that that limit gives 0, then some sources might use this, what we call little o notation. F is little o of g. Now, if the limit gives 0, it's still a finite constant, and it still satisfies the definition from before. And so you still have the case that f is big O of g automatically in this sort of situation. For this course, all we'll need is big O notation, but I kind of wanted to bring this up so that it's familiar to you in case you see it again in your life. Okay, so I kind of alluded to this before. We've talked quite a bit about this, but big O notation is really helpful in having us compare different kinds of growth. So for example, all of these different kinds of functions, some of which are kind of well described in the graphs back here, right? We have something that grows exponential in that red curve that's going up there. We have something that increases linearly. We have a log function, a root function. Every single one of these grows without bounds, right? Like every one of those goes up towards infinity, but they do so in different ways. They have very different behavior of how quickly they grow. And big O notation helps us to quantify, right? It gives us, as I said, like a bit of a hierarchy of what comes before what. Which of those functions is on the order of which others? And the curves here that are flatter are going to be on the order of the curves that are less flat. So like the linear one is going to be on the order of that exponential looking one. And that square root looking one is going to be on the order of that linear looking one and that exponential one, and so on. And any two parabolas are going to be on the order of one another because of the comparison, right? Like the similar behavior. Any two exponentials that are, of the form e to the 2x or whatever are going to be on the order of one another. But it's about this comparison as n grows large. So let's do some examples so I don't just blab on forever. Let f of n equal n cubed plus n plus 7. We are wanting to show that f is on the order of n cubed. Okay, so here's what we want to do. Most of the time, it's good to set up that ratio and then test that limit to see if it yields a constant, because that is going to be enough to show that comparative growth. So I'm going to say set up the ratio and take a limit. And if we do, we're going to say n cubed plus n plus 7. I'm going to put that over n cubed, and we're going to take the limit as n goes to infinity. Now, you can remember all sorts of ways from first year calculus how to do this, but it's probably easiest just to divide through by the n cubed, and you get 1 plus 1 over n squared plus 7 over n cubed. And of course, these two, right, as n gets very large, 1 over n squared gets very, very tiny, and 7 over n cubed is even tinier. This goes to 0. This goes to 0. This whole thing does, not just the bottom. The bottom's getting very large. And the limit gives you 1. And 1 is a constant as n goes to infinity. And therefore, we have that the conclusion is true. We have that n cubed plus n plus 7 is on the order of n cubed as n grows to infinity. Yeah, that's all there is to it. And what this is essentially saying is relating to the fact, right, like n cubed plus n plus 7 is going to grow in a really similar way to a basic n cubed function. Maybe in certain sorts of situations, when you want to know about how big an expression is going to get, but maybe you don't care about the little details and so on. Maybe it's enough to say, hey, this function grows like a cubic does. Right? That can be more helpful in certain situations. We're going to be talking in a little bit about, right, the number of operations it might take for a computer to execute something. And oftentimes that's something that we might be interested in, as in like, well, does the number of steps grow polynomially with a problem? Does it grow exponentially with a problem, which means that there's going to be more work relatively as a problem grows in size, right? Having this way of measuring asymptotic order can really help to solve those problems. Okay, here's the next example, which is a little bit interesting, but it's not that interesting. I don't know. Which is true. Ln of x is on the order of ln of x, or ln of x is on the order of ln of x. And of course, here we mean as x goes to infinity. Okay, let's think about this. If we think of what on the order means, it means this function grows, the first function grows no more quickly than the second function, or a function of the type of the second. Okay, so toss this around for a little bit. But if I'm thinking about it, if I have x, and then I compare ln of x takes x and then makes it, right, it kind of stretches it out and makes it flatter. If I take ln of x, it's going to do more of the same. So I think that after a little bit of deduction, you might settle upon this second one. That this function here, ln of x, might stretch it out even more. It might grow even more slowly than regular ln of x, which means, therefore, it grows no more quickly than ln of x. So we suspect this to be the case. We suspect this one to be true. You could try the other one if you wanted to, and you should find that it doesn't work out. Let's test it. Okay, so if we want to test it, that means I'm going to take ln of x. I'm going to put it over ln of x, and I'm going to take the limits as x goes to infinity. Okay, and you might stare at this for a second and wonder what the heck to do. As I switch to my green pen here, you put in infinity, or you imagine x getting very large, more accurately. Ln of x also gets really large, so ln of x goes to infinity as well, which means that ln of that also goes to infinity. So the top is going to infinity, but the bottom is too. This is infinity over infinity, and before you just say it's 1, or before you say it doesn't exist, or anything like that, I want you to think back to the last time you were in the hospital. I don't know where I'm going with this. We need L'Hopital's rule. That's what we need. So remember that, right? Some students forget that we do have ways of dealing with indeterminate forms for limits. Infinity and infinity don't just divide out, right? That is meaningless until we do more work. It could be 0, it could be infinity, it could be anything in between. So use L'Hopital's rule. That is going to come back here. And so you need to know how to use it and be ready for it. And remember, L'Hopital's rule is valid whenever you have an infinity over infinity or a 0 over 0 limit. So we need to use that. L apostrophe H is the little, I don't know, logo I use for my old teacher, my old calculus teacher used to say, L'Hopitize it. So, I mean, you could say that if you want to. Anyway, what we're going to do is take the derivative of the top and put it over the derivative of the bottom. And if we do, we get 1 over ln of x times 1 over x. Thinking about chain rule in the top, right? The derivative of ln of x is 1 over ln of x times the derivative of what's inside, that's 1 over x. And then I have to put that over the derivative of the bottom, which is 1 over x. What's nice about that is that you see a 1 over x there and a 1 over x there. So those can cancel out. And it becomes pretty clear that 1 over ln of x is going to go to 0. Ln of x is going to get very large. You get 1 over very large, and this goes to 0 as x goes to infinity. So this is a constant. And therefore, we have the conclusion. We have that ln of x is indeed big O of ln of x as x gets very large, okay? And in fact, we see that ln of x is also little o of ln of x as well, since the limit was 0. Okay, I should put an end bracket there. Again, I just want you to know what little o means, and it turns out this is the case here. It turns out that ln of x grows much, much less quickly than ln of x itself. So you can say that it is little o of ln of x, if you would like. But the important part is that we have that the one is on the order of the other, okay? If you worked out the other one instead, what would happen is that this limit would be flipped upside down. If you tried to evaluate it, you'd end up getting infinity, which means that you would never be able to find a constant in that original definition, which should make a lot of sense, I think. All right, so let's see where else I'm going to go with this. Yes, we can also use this notation to describe IA, infinitesimal asymptotics. So that is where the parameter involved is not getting very large, it's very small instead. That can be really useful for a few different contexts, including, like we were talking about Taylor's theorem and the error involved if you are evaluating a polynomial approximation of a function within some certain radius, right? And you have that error might decrease as the distance away from the center point decreases. It's some small quantity, so hopefully you're not that far away from the center point. You can talk about that error in terms of asymptotics. And we actually will in an example here. So let's kind of put this together in a definition, but it really doesn't make a big difference. It's pretty much exactly the same definition as what we did above. The only difference is this. So we have that f of h is on the order of g of h if there exists some delta. Looks a little bit scary, but don't worry. Think about this like some threshold again, such that whenever h is smaller in magnitude than delta, so whenever h I'm going to write this down because I think it just helps to get it out of the math for a second. Okay, i.e., if h is small enough. The first definition we talked about if n was large enough, if there was some threshold beyond which a certain relationship was true. And here we want to do the same thing, but we need to make sure that h is small enough. So the delta is like a threshold in the size of the h. So if within that threshold, with h tiny enough, we have that the same relationship is true, that the size of f is less than or equal to k times the size of g for some positive constant k, then you have that that is true, that f is on the order of g. But this time as h goes to 0, or as treating h as a small parameter. You can, again, determine that this is true by, again, evaluating a limit. But this time, it's going to be where the top is going to 0 and where the bottom is going to 0. You take a limit not as n goes to infinity, but as h goes to 0. If you get a constant, then that means that the f and the g must decrease in at least roughly the same sort of way. And that's when you have that f is on the order of g. Okay, so really similar justifications, but a little bit different. We're going to show that the infinite polynomial right here, each of the an here are positive constants. This infinite polynomial we're going to show is on the order of h squared as h goes to 0. Okay, let's try it out. Well, let's set up a ratio and take a limit. If you do that, I'm going to just write this out. I'm going to write this out as kind of like just it looks like a sum from 2 onward. So this is a2 h squared plus a3 h cubed plus a4 h to the 5, or 8, not 5, 4, plus a5 h to the 5, and this would go onward as long as you would like. If I then divide this, I need to show that it's on the order of h squared. I guess I'm kind of covering that up, so I'll redraw this. On the order of h squared means that I want to divide this by h squared. Then I'm going to take a limit as h goes to 0. Okay, so let's see here. If I do that, it seems pretty obvious that I can divide through by the h squared into each of these terms and get a2 plus a3h plus a4 h cubed plus a5 h to the 4 and onward. And then as h goes to 0, it's not hard to see that this is going to go to 0, that this is going to go to 0, that this is going to go to 0, and all of the terms that come after that are going to go to 0 as well. And what we get here in the end is nothing more than a2. And a2 is defined in the first place as a positive constant. So thus, it is on the order. I want to be a bit more precise. The infinite polynomial. The infinite polynomial is on the order of h squared as h goes to 0. With 2 exclamation marks, not factorials there. So that's interesting, right? We're saying that if h is something small, then you can have all of these higher powers added on to h squared, and the result still grows, or still goes to 0 now, quite like a regular parabola would. That's actually really big, because this, I did this example for a reason. It taps into something that's really similar to Taylor's theorem. And what this is going to do is it's going to give us a really interesting and useful way of expressing the error associated with our Taylor, our Taylor approximations from earlier. Because essentially, I want you to think about it, right? There are a couple ways to do it. You can look at the error term, which we're going to do right here, or you can simply think of the exact value of a function is equal to its infinite expansion, its infinite Taylor expansion. If you cut that off at a certain place, well, you're off by the other terms. I would like a way to describe those other terms, so we can either do so using the error formulation from before, or, well, we're going to talk about it more here. Okay, so I would like to just have you recall for a second our example from back in the Taylor polynomial section from 2 lectures ago. Recall that the Taylor polynomial for e to the x about x equals 0 is given by this. This was our Pn of x, if you remember. It's our nth degree Taylor expression or approximation, and this is the associated error, which we called Rn of x. And it was a piece that depended on one power up, one derivative up, evaluated at some c that was between the center point and the x, and that's just what it was. A little bit gross to write down. Okay. But watch. That c, whatever it is, it's some specific number between x and whatever the center point is. For e to the x, that center point was just 0 with this expansion. So it's just some number, and the derivative, the n plus first derivative evaluated at that, is just a number. Also, n plus 1 factorial, doesn't matter what you have for n, that's just a number as well. It might be a really big number. The point is that this quantity, that derivative evaluated at whatever c is, and n plus 1 factorial, is just some constant. And because it's some constant, I can take that constant times x to the n plus 1, right? A constant coefficient of x to the n plus 1. And I can show very easily that it is on the order of x to the n plus 1 itself. All you'd have to do is take that constant times x to the n plus 1, put it over x to the n plus 1, and then take a limit as x goes to 0. And clearly, the x to the n plus 1s would cancel, leave you with that constant, and that's a constant. So you'd show that that ugly term is nothing more than something that's on the order of x to the n plus 1 as x gets really small. So what we can actually do is take this thing, take this Taylorization of e to the x, and instead write this: 1 plus x squared over 2 plus dot 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 plus x to the n over n factorial. And then rather than remember what this error is, and I still want you to know what it is, and I still want you to understand where it comes from, but we can just write big O of x to the n plus 1. And the way that I want you to read that is some error that is on the order of x to the n plus 1 as x goes to 0. That's all I want you to do, to think about it, right? To understand that that piece goes to 0 in the same sort of way that the n plus first power of x would. And I said one thing's for certain. This is definitely easier to write down. Which is a little bit funny, but a lot true. It's much nicer to think of that as some more general, simpler quantity that just increases in the same way that this function does. The other way that I said that we could look at it is, imagine you have all of those different, right, the infinite polynomial. If I wrote down something like e to the x equals 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial, and so on, imagine that I took an approximation that's second degree. That means lopping this off and saying, that's good enough. The error associated with it are all of the unclaimed terms, everything after that, right? These terms right here. So imagine if these terms were our approximation If those terms are approximation, then this is the error. It's the rest. It's the remainder and the error. And just like in the last example that we did, we have an infinite polynomial of x cubed, x to the 4, x to the 5, and so on. And in the very same way as the example from the last page, this is just on the order of x cubed due to the fact that you can take that remainder infinite polynomial, put it over x cubed, and show that it gives you a constant as x goes to 0. We can see from the example on the last page that this is big O of x cubed. And then that agrees with what we just said above. So you can kind of look at this both ways, but I want you to really understand that, okay? So I'm just going to say consider this. Just as one kind of bonus example at the bottom here. And you can start to see why this is a little bit of a powerful thing. Sometimes it's just useful to have a simpler way of quantifying these kinds of concepts. So a little bit of a long, we're up at 36 minutes and a half and so on, but hopefully you've been able to follow along. It's a little interesting to talk about, right? Relative growths of functions. Or I guess if the parameters are very small and going towards 0, comparing how different functions go to 0. Do some go more quickly, do some not. We're going to start applying this to some different things when we talk about computer math. So we have a couple of interesting lectures ahead. Basically, how do computers represent numbers? What are the decisions that computers have to make to, say, round numbers or chop them? We're going to talk a little bit about that. And we're going to talk about like the structure of what are called floating point representations in computers. And then describe a little bit about how to measure the number of calculations for something. And to that, we'll definitely be applying this kind of stuff, this big O notation stuff. So hopefully that's good. Feel free if you have any questions to contact me. I hope this was really good, and I look forward to the next lecture. So for now, I bid you all a fond farewell. See you soon.